Here we go. Today, we are going to hit the last part of the topics that we have right now. First thing I thought it might be helpful for you guys to do is talk about kind of like all the subjects that we have right now and a little bit how they're interrelated as it stands. We'll be kind of quick with this. The first subject that we discussed, where did that thing go to write on the board? I was literally just using it. That's embarrassing. Oh, there it is. Okay. Was torques into sum of torques. What is a torque? And of course, what if sum of torques equal to 0? These were translated as were our bridge problems, aka our equilibrium problems. Okay. The next subject matter that we discussed, of course, was what if it's not equal to 0? And then, of course, it's equal to I alpha. So you have individual torques, you have summing torques equal to 0. And of course, alongside that, if you're doing equilibrium, sum of forces equal to 0 means there's no acceleration. Okay. Sum of torques equals I alpha was dynamic, and this is kind of where our quiz hit right here. Then, of course, yesterday we started talking about conservation of angular momentum. Of course, angular momentum being I omega. And the thing I told you to let you know that this was going to be the case is, of course, that sum of torques is equal to 0. So how do you separate, for example, the bottom line from the top line? It is simply this, whether or not it started off moving or not. Okay? If it didn't start off moving, you got a bridge problem. You got an equilibrium problem. If it did start off moving, boom, you've got a conservation of momentum problem. Also, I've used the spinny thing a lot, and I recognize that you probably do not have a spinny thing at home. If you have never seen this, everything that I have done in angular momentum 100% works for a spinny chair that you can find anywhere. So you can start off with a large angular momentum and pull your legs in and out, and you can change your you can change your angular speed while conserving angular momentum. Just looking at an example. I had a problem that I kind of changed today on 8.5. I did change a fair amount of problems on 8.5. If ever that happens and you've done work already on 8.5, you can leave it. You do not need to touch it. Change it. I don't expect you to change all your numbers correspondingly to that. And if for some reason you don't have a good answer key because you changed number 3, I don't know what it is, shoot me an email. I will find out what that answer was previously. I'll let you know to check that type of thing. So I say that because one of the problems I think on the homework, I think it's number 4, changed from this arbitrary cylinder that you drop a piece of putty on. You were supposed to essentially see that it was kind of like a pottery wheel thing spinning around, and you drop something on it. What do you expect to happen? Now it's, you got a spinny wheel, you got a spinny chair, a rolling chair, spinning around, and you drop a duck. And you drop a duck, and the duck lands somewhere away from the center. What do you expect to happen to the angular velocity? What should you expect to happen to the angular velocity? What should happen to the angular velocity? If this was spinning, assuming it was spinning forever with no rotation, and I dropped the duck at some distance from the center, it should slow down. Yes, because you now have more moment of inertia, right, on that object. What angular momentum would the duck have originally if you drop it from above? Sorry, and think about it on the rotation. How much angular momentum would it have? Yes, it would be 0 because it's not spinning around here. It would just be dropping straight down. All right, now today, good news, bad news. It's the same news. We're doing energy again. Now again, good news, bad news, but it's the same news. Energy actually doesn't have anything new. Energy is scalar. There's no potentially rotational energy. It's just energy. So if you had a situation, hold on, I'm recording, good, okay, where a object goes down a hill in energy, what type of, there were 2 main ways that we tackled energy. Do you remember what they were? It's been a minute. Don't blame you. Okay? It's been a minute. Okay? It started off, what does the subject of energy start off with? The definition of, all of energy revolves around this concept. What's that? Work. Correct. Okay? The equation for work, of course, was force displacement, all going in the same direction. In a nutshell, energy is just this. Hey, if something's getting pushed this way, and it goes the way that we expect it to go, energy is spent. right? Like if you have a, what do you expect to do if I let go of this ball in my hand? So when it does what we expect it to do, and work comes out. Work is positive when it does what you expect it to do. Work is negative when it goes against the thing that you expect it to do. Yes? Out of that was the work kinetic energy theorem. If you add up all the works, I go, hey, I put 10 joules in here, 20 joules in here, 30 joules in there, that's 60. But we take 10 joules off over there. That 50 joules, where does it end up in? Change in kinetic energy. If I have more energy than I started with, I should be going faster. I should have more kinetic energy. The one that I really want to highlight that we're going to look at is conservation of mechanical energy. All the mechanical energies initial equal all the mechanical energies final. What are, let's do energy tree again real quick. Just as a review, you don't have to write this down unless you really feel like you need it. I'm just going to put it up here to review with you real quick. What are the two branches of energy? If you don't remember, I'm happy to help, but so feel free to guess. What's that? Mechanical and non-mechanical, correct. Cool, mechanical split into two categories. What are they? Kinetic and potential, okay? Kinetic, of course, has its own equation, but I'm going to wait on that in a second, or actually I'm going to do this, and you're going to be sad a little bit later because, well, we'll find out. It's like 1/2 mv squared, yes. Okay, potential. Potential was the potential to do work, and it was specifically the potential to do work by two particular forces. What were they? Gravitational potential energy, which was calculated by MGH, and potential elastic, which was 1/2 k delta x squared. So, of course, when we conserve mechanical, actually, let me finish first. What are the 6 non-mechanical types? Throw out any of them. Light. Sound goes with it, yeah. Chemical? What's the one that goes, thermal is right, but what's the one that goes chemical? Nuclear. If you ever forget that, by the way, in a nutshell, chemical, anything that happens to the electrons on the outside of the atom. Nuclear, anything that happens in the nucleus. There you go. Okay, light and sound, you can see light, you can see it. Sound, you can hear it. Thermal is correct. Thermal is basically this: kinetic energy for a bunch of crap at the same time. It's air. Say the temperature in the air right now is based on what's the kinetic energy of the air. When it was cold outside, the air wasn't moving as fast. When it's hot outside, the air's moving very fast. That's what thermal is. We're missing one. Do you remember it? Electrical is correct. Electrons moving through a wire. We will talk a ridiculous amount about those if you come to physics 2. Okay. That all being said, this was our situation, and you can probably see maybe where this is going. None about this is actually going to change whatsoever. If we want to do conservation of mechanical energy up on the right side there, all we got to do is how many types of mechanical energy are there? 3. What were they? Kinetic, gravitational, and elastic. And now let's focus specifically on one to actually see where these things are, in fact, going to change. This kinetic energy right here, this would be the mass times its velocity. So you know, essentially, that an object has kinetic energy because it's going somewhere, yes? More specifically, that's when we were treating the object like it was all at one spot. So really, it's if you imagine the center of me is going somewhere, you would have kinetic energy, yes? Well, is the center of me going anywhere right now as I spin? So by that logic, would I have any kinetic energy? No. But are there pieces of me, like my elbows, fingertips, fingers, that are in fact do have a speed or do have kinetic energy? Yeah, it's a scalar thing. So that probably means that this needs a particular subscript on it. We'll call this kinetic energy translational. So kinetic energy translational is the one that we have always dealt with. So there's probably a new type of kinetic. Kinetic energy, if you had to guess, what's the label on it? Rotational is correct. Let's try to make it a little bit bigger so it's a little bit easier to see here. Well, I'll put it up here. I'll write it again in just a second. And all you need to do once again is use your analogies. If kinetic energy is 1/2 mv squared, guess what kinetic energy rotational is? 1/2 times what? I times omega squared. So to show you this stuff in action, to show you stuff that this really matters, let me demonstrate this in two ways. Number one, I could show you videos, but I don't have a great video, and you get it. If you ever seen parkour, when they do the crazy jumping and the whatnot, and spinning through the air and finding creative ways to get from place to place, a very staple of parkour is something they do if they fall a very long distance and hit the ground. Okay, what does it seem like every parkourist does when they hit the ground? They always roll. Okay, and you might have thought, okay, which I probably did when I was first thinking about this stuff, that's just to look cool. Okay, it does feel like that's a very parkourist thing to do. That is actually not true. The act of rolling actually does make it easier on the joints, and you hit the ground less hard when you do that. Okay, I'll explain that through another example, and we'll come back to that a little bit later. According to just conservation of mechanical energy, coming back here, if I drop something from this height and I let it roll down a ramp, before we got to this stuff, what type of energy would be up here initially? Let's knock out all three of them, talk about it. Would it have gravitational? Yes, it would. Okay. Would it have kinetic? Assuming I dropped it. Let it go, sorry. We're at the top, I'm just letting it go from 0. So would it have kinetic immediately? No. Would it have elastic? Okay. Then it comes down to the bottom right down here, and we figure out how fast it's going. Okay, at the bottom, would it have gravitational? Not if that's where we put our 0, which probably makes the most logical sense. Yes, so no gravitational, we put our 0 there. Okay, would it have kinetic? Yes. Would it have elastic? No. So according to this, if I take two different objects and I let them roll down the ramp, which one should be faster, according to this? By the way, these objects, while made of different materials and different shapes, are in fact the exact same mass, although you'll remember from energy, does mass actually matter with the speed that you hit the ground at? No, mass doesn't matter, but they are in fact the exact same mass. So, according to that, would they, starting here, have the same gravitational and initial energy? Yes. So should they hit the ground with the same kinetic energy? Yes. So based on that, which one should be going faster when they hit the ground? They should be exactly the same. And what you'll find in just a second is that's not the case. Let's run some races real quick and see if you can't figure out what the separation between the two of them is. Okay, which one do you think gets to the bottom first, aka the fastest? We got the disc. He's got a face on him. It has a Bob vibe. Let's go Bob. Okay, and let's go the metal ring Jerry. Okay, who do you think wins? Let's vote on this. Let's vote, or you can say same, I suppose. All right, how many think Bob wins? Okay, Jerry? All right, then how many think it's a tie? All right, here we are. Let's go. Yes, let's go. All right, here we go. Okay, let's try again. Very good. All right, let's do another race. Okay, I'm not naming all of these. We'll just use the objects in question. Here I have a tennis ball and a bocce ball. Okay, they're both yellow, if that matters to you. Okay, we're going to race them, put them right next to each other up here. Once again, the question is, which one do you think wins? The goal, by the way, of this process is, who cares if you're right? We're trying to see what is it that actually separates them. There is something that actually separates them. All right, which one do you think wins, the tennis ball or the bocce ball? Let's vote on this again. How many say tennis ball? Okay, bocce ball? Same. Oh, that's unfair. Pretty obvious that it wasn't even close. It was absolutely the bocce ball thing here. Okay, let's try again. How about, let's go, let's compare here. Let's go, so Jerry and the bocce ball. Wait, what were the two slowest? What were the two slowest? The two slowest were Jerry and the tennis ball. Who wins out of these two? Jerry wins. Okay. About the same. And arguably, it should be the tennis ball. So let me cheat a little bit, and so the tennis ball is going to use a cousin. You're real close though. It should be the tennis ball, but only by a hair. Very, 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 very low. Okay, so let's do this one then instead. The two winners were Bob and Bocce Ball. Who you got here? We got Bob. Bocce Ball. All right. Just by a hair, it is in fact Bocce Ball. Okay, here's the trick one though. What if I go bowling ball versus Bocce Ball? See if you can spot this. Let's see if anybody has figured out what it is, and let's actually vote on this. Okay, how many of you say Bocce Ball? How many say bowling ball? How many of you say the same? It should be exactly the same. Now there are some small discrepancies you might have noticed. Let's say, oh, that's bowling ball. No, it's about the same. The issues that are probably dealing with here is Spainar's imprecise nature of letting go of these. See if I can let them go in the same spot here. Yeah, it's hard because I gotta get them same. You can see the Bocce Ball. It should be about the same in that particular case. Any ideas? What is the separation between which one's winning and which one's losing? Yes.
Material.
No, it's not material. Yes.
Density.
Closer, but not quite. Moment of inertia is correct. It is moment of inertia. Which one won between the disk and the solid ring about the axis? It might be helpful, by the way, to pull up the corresponding chart on anything. Which one won? It was Bob, wasn't it? The disk, and if you'll remember equations, 1/2 mr squared, mr squared. Okay? Which one of these has more mass closer to the center? This guy does, so it has a smaller moment of inertia, and this guy seems to win. Okay? In the race between the tennis ball and the bocce ball, okay, you got 2/3 mr squared and 2/5 mr squared. I believe, I don't remember what they are off the top of my head, but here's how you can figure out yourself very quickly. Okay? All you do is you go, which one has more mass further away? This one has more mass further away, right? Of its own mass, not individual mass. And so this guy is your higher one, so this is your 2/3. This one is your 2/5, and so which one's smaller? This guy here, so which one wins? This guy here, okay? Then you notice potentially a weird thing, okay? You can start racing them, like I said. We took the two winners. This guy was, of course, 2/5. This guy was 1/2, so arguably, according to that, which one should win? 2/5 should win on that particular front, and you see why these are really darn close over here, because this was 2/3 mr squared, and this is just mr squared. The other piece of this puzzle that's kind of messing with numbers a little bit on this is the fact that friction, we are assuming, should not be doing things, and it does mess with things just a little bit on that particular process. Now, the last thing I will show you, and you will see in the math, and this is the last thing we're doing, I promise we're almost done, is this, okay? Why should these then get the same thing? Do they have the same radius? Definitely don't have the same radius, which means this one should have a larger angular velocity. Okay? Why doesn't it have a larger velocity? We'll see that in the math in a second. And of course, while this also has a smaller radius, it also has a smaller mass, which means do they have the same amount of gravitational energy to begin with? Do they have the same amount of gravitational energy at the beginning right here? Okay, let's do some math, but actually, right before math, let's answer the question. Why does the person roll when they hit the ground? Well, this is what it used to be. Person slides around the ground. But what we weren't worried about previously is we weren't worried about this object having any rotation to it whatsoever, right? Friction in this example, we always had to assume was 0. And actually, in this particular case, friction is not 0, which is good because it causes that rotation. So how does this situation change for you now? Well, let me ask you this one question once again. Is there any gravitational potential energy of a bowling ball about to go to the ground? Is there any gravitational energy? Yeah, absolutely. Okay. Is there any elastic energy at the top? Nope. Is there any kinetic energy translational of the bowling ball at the top? When is there going to be translational kinetic energy? When the center of mass is moving. This is me having kinetic translation. Okay. Is there a rotational kinetic energy of the bowling ball at the top? Nope, because it's not rotating. This, by the way, is me having rotational but no translational. And finally, this is having both. Why do I have translational? Center of mass is going somewhere, and you can see it as rotational, and that's, of course, what you see with the bowling ball at the very end. So there's still only gravitational initial at the beginning. Is there translational of the bowling ball at the end? Yep. So I'm going to say translational final. And is there rotational final? Yes. Why does the parkourist hit the ground and roll? Because if they take their energy here by making themselves roll, this is kind of weird but also true, by making themselves roll, they will not hit the ground as fast. The more they can make themselves roll, the more energy goes over here, the less energy you will hit the ground with over here in this particular case. So let's do some math on this. Here's the thing. Let's go. The bowling ball has a mass of 5 kilograms. It has a radius. I'm making some numbers up here, but they really don't matter, as you'll see in just a second. I don't know. What do we got? Let's see. Bowling ball has a radius of about 12 centimeters and starts from a height of about, I think I should probably be like 15 centimeters. You might note, by the way, that that's not to the center of mass, which I should technically be going to, but also its center of mass is going to also be that much distance above the zero when it hits the ground. The question is, how fast is the bowling ball going at the end? The way you'll set up this problem is, like I said, you can see it right here, identical to how you would have previously. Conservation of mechanical energy. The only thing that is now changed is we have a fourth version of mechanical energy in the form of rotational in this process. So from here, I'm going to fill in individual equations. What's the equation for gravitational? mgh. So I'm going to say mgh initial. What's the equation for translational? mvf squared. Plus, what's my equation for rotational? Omega squared. Now, I have a lot of the variables up here already. I'm looking for this one. Obviously, these variables over here get a little bit wonky. So the first thing that we want to do to make some translation things is, okay, what moment of inertia should we be using for the bowling ball? Is that the 2/5 one? Sure. I'm not positive. I want to make sure to actually not lie to you. Ooh, I did lie to you yesterday. I forgot about that. I told 6th hour the backwards, and I was like, whoa, okay. For the sake of the homework, I told you aphelion and perihelion are switched. That's not correct. Did you see that too late? I'm so sorry about that. Perihelion is, in fact, the closer one. Aphelion is the one that's further away. I apologize. I had them switched. All the math tracks, by the way. Nothing's wrong with the math. I just put the wrong variables in the wrong spot naming-wise. I did that in 6th hour, immediately. I was like, ooh, I did that wrong for them. All right. Here we go. Here we go. 5th hour. Last work. I think it's 2/5. I'm pretty sure it's 2/5. Did someone already look it up? It is 2/5? I'm sorry. I thought you guys didn't. All right, I got you. All right, 2/5. So right over here, you're going to go 1/2 times, of course, 2/5 mr squared. And then the rest of this stays exactly the same. And then over here, I would also have omega squared. Does anybody see a nice simplification that already starts to happen here? Masses cancel immediately. So bocce ball versus bowling ball, does it actually matter how much mass either one has? No. And the reason why for that real quickly is this, because yes, more mass is going to give you more energy to begin with, but also that inertia thing, more mass makes it harder to spin at the end. So you get twice as much energy, but it's twice as hard to spin. You're going to get the exact same result. It's like if you have a sumo wrestler twice the size of Spainauer, if you push the sumo wrestler twice as hard, you're going to get the same effect as if you shove Spanauer, blah, 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 inertia. Our last issue right here is this. I'm trying to get this. Oh, how do I deal with that? If only there was an equation that translated between linear, rotational. You've seen this before. What is our equation between linear variables and rotational one? Tangential equals omega times r. So omega equals velocity over r, yes? So I'm just going to go back here and say I substituted omega is velocity over r. Now notice that I substitute before the square. Once you square this parentheses, don't forget everything inside gets squared, yes? So this should actually shortcut if you want to do this immediately to v squared over r squared. And now, what other simplification actually matters? R's also cancel. So, like I said, bocce ball and bowling ball, they have different masses and they have different radiuses. Does it actually affect the result at all? Nope. I gave you these two pieces of information. You don't even need to know what they are. So here we go, just doing the math to simplify, and we're all done. What we have here is GHI is equal to 1/2 VF squared plus, let's simplify over here. How do my fractions simplify? 1/2, 2/5. Yeah, twos cancel, so 1/5. And if you look at all this stuff canceling over here, the only thing actually left over here is 1/5 velocity final squared. So what do you got to do between these two terms? We remind ourselves of the dumb common denominator crap. What's your common denominator here? You got 10. So this, of course, is going to be, and if you can do this in your head, please feel free to, 5/10 over 2/10. So you're going to end up with GHI is equal to 7/10 times VF squared. And I think you got it from here, but let's finish her off. How do you move the fraction to the other side? You can divide or preferably just reciprocal, 10/7. 10/7 GHI is equal to velocity final squared. So square root both sides. And here we go. 10/7 times G times 0.15 meters, the square root of the whole thing. 10 divided by 7 times 9.8 times 0.15, square root the whole thing, 1.45 meters per second. Would anything about that have changed if we had done the bocce ball? So what is it up here that is actually changing? Like if I go from bocce ball to tennis ball, mathematically, we're not going to do it, just show me real quick. What does change in all of this work if you are doing a tennis ball instead? So specifically within the moment of inertia equations, the fraction. That fraction right there. Yes, had you done tennis ball, that would be 2/3. You would have ended up with 1/3 here. Your common denominator obviously switches. You'd end up with 6/5 over here, which is a lower ratio than this one, and therefore the tennis ball loses out to the bocce ball and has a lower overall speed at the very end. Questions, concerns? Okay. As complicated as this subject is, I want to be very clear about expectations as far as the test is concerned. I don't like to give you just, this is how you do a problem, copy it down a few times, but that's almost exactly what a lot of these are. Only exception to that being like a problem where I tell you all the stuff to get I, all the stuff to get omega, and I asked what its rotational kinetic energy is. Oh, I forgot to mention this. If you had to guess, what is the units for rotational energy? Gentle reminder, what are the units for every other energy? Joules. Yes, it is still joules. They do in fact cancel out the exact same way, and they do end up as simplify the exact same way, and they still end up as joules. Okay. Remind me again, why does a parkourist roll when they hit the ground? More energy in. Rotational means less energy in. So they don't hit the ground nearly as fast when they roll. What's that? number one, they can't start actual rolling in the air because they can't provide torque to themselves yet. That's that conversation we had yesterday about the person diving, rolling through the air. Now they can control, through conservation of angular momentum, they can control how fast they spin in the air, but they have to land, and they regularly do. And if you ever go into parkour or mess anything like this, they will teach you that basically when you land, you want your center of mass in front. And the reason you want your center of mass in front is because then when the ground hits your feet, it will cause torque, causing you to rotate in that particular process. Versus, and you kind of expect this, if I was dropped from the ceiling and I don't put my center of mass in front of me, if I leave my center of mass what it is, you're going to expect me to hit the ground like this. That's not going to cause rotation. I'm going to hit the ground with the full velocity and force that I'm going to feel everything all the way through my bones. So they do it for a legitimate science reason. Of course, they didn't do the science ahead of time, they did it experimentally, but that's a good way to do it as well. So yeah, they will tell you hit the ground with your center of mass in front so that when your feet hit, they cause rotation, and that causing a rotation gives you rotational kinetic energy taken away from translational. You don't hit as hard. There you go. What's up?
So,
hold up real quick. I'm done with the video, unless you want to, yeah, I'm done.